the Orion 2 and its design and programming and other topics. We'll come to that in a moment. Can I just remind you that the next meeting is on November the 20th, when Doran Swade, who requires no introduction, Doran Swade will be talking, giving us a talk with the title "The Shocking Truth About Charles Babbage and His Calculating Engines." I don't know whether this is quite news of the world standard shocking truths or what, but Doran, I think this is probably based on his PhD research, which he is in the process of having examined at the moment. So this will be hot off the press on November the 20th, and that will be either here or in the lecture theatre at the museum. So if we can come to today, the Master of Ceremonies really is Frank Taylor, who I certainly have known for a good many years. I can't remember, it must be probably 20 years, Frank, since perhaps you and I first met. I've met Frank in the BCS, on BCS committees and activities of that sort. But today he's here as one of the design engineers that worked on Orion 2, and then subsequently spent 11 years working at the NCC, and then the last 24 years, he tells me, of his working career creating 2 successful small companies that he was then able to dispose of. So, Frank, we're delighted to have you and your colleagues here. I'll leave you to introduce your colleagues as we go along, and we look forward very much to hearing the story of the Orion 2. Thank you.
Thank you, Roger. Well, good afternoon, gentlemen. Providing at the master list, which I can manage to do. This is the beginning of the story of today's talk. Most of you will know that around 1994, 1893 or 1994, Ferranti Limited, as we in fact knew it, the family company, sadly went bust. That triggered me to write an article in Computer Bulletin, many of you may just remember, titled Requiem for Ferranti, in which in fact I gave a thumbnail sketch of what Ferranti has done in its 30-odd years involvement in the computer field. That article was subsequently processed, and I think I'm picking the right word, by Hamish, who's here, who put it in his ICL anthology, the first one of the 2, and was seen by a lot of people. Subsequently, Alan Thompson, who's over here somewhere, there we are, picked up Hamish's article, in which I had stated that the Orion 2 project really showed what Ferranti could do. I believe Ferranti bowed out with a tremendous burst of effort before the ICT takeover, and this project showed what Ferranti could do. So effectively what Alan said, in rather more polite terms, was, would you like to put your mouth where your pen is with the help of a few more colleagues? So here we are. That's how we got here today. The beginning of the story of today's story. Now let me move on to the beginnings of the Orion story. Around June 1958, give or take a month or 2, Ferranti set up a working party to plan an own-brand computer. Most people will know that all the computers made by Ferranti prior to 1958 were effectively designed by Manchester University, machines like Mark 1, Mark 1 Star, Mercury, and of course the Atlas as well, all designed by the Manchester University team, and Ferranti had the manufacturing rights, but they were joint efforts.
But not Pegasus? Not Pegasus. Pegasus was different.
Pegasus, haven't I? Yes, my apologies. Thanks for the corrections. There were on-brand machines, apart from the military ones, like Apollo, before, in fact, Orion. So you've corrected my wrong thought. Thank you very much indeed. Anyway, whatever the background, around 1950, to get correct if I'm wrong, Ferranti planned to design and make an own-brand medium-sized machine, which would not be a result of the Manchester University Ferranti Cooperation Agreement. Part of the thinking behind this was that the Atlas market was always seen as small. Some academic, I believe, did a calculation around that time, early 1950s, and calculated that 5 atlases of Atlas, whichever you want to call them, would in fact do all the computing which would have required in the UK. I have no comment on that particular statement. It was decided at some point in 1958, and Ted may want to come on to this later, that neuron circuits were to be used, and there was considerable influence, in fact, in this area from my first boss at Ferranti, Mr. Gordon Scarrett, otherwise known University of GDS. The working party set up to build a machine on top of these neuron circuits consisted of Ted, who's here today, Ken Johnson and Charles Lindsay, who I don't think are here today. Put their hands up if they are. No, they're not here today. Ted included multi-programming specification. I'm sure he's got to touch on that. I'll just give you a few pointers to what we can later. I believe Orion built on at least the principles, if not the detail, of a Pegasus-derived instruction set. But it did have core store, immediate access store, random access store, instead of the delay lines, which of course appeared in Pegasus. Since Ted mentioned Persis, I believe also delay lines. Okay, the machine, just final point, had 6-bit characters. It wasn't by this time byte-oriented, and a 48-bit word, because that gave quite a lot of bit positions for manipulation, indexing, and a reasonable instruction set. And it would be wrong of me to go further in that area, because that I think is what Ted was talking to us about a little later. I'm just setting the scene and introducing what will become in a moment. With regard to getting a decision made, a decision was made after that working party did its work. The Orion 1 development, in fact, proceeded apace. And the scenario, late 1961, early 1962, and I wasn't involved in this, so my dates might be subject to a tolerance, was that the Orion 1 development was grinding on. There were inherent problems at the engineering level, and Chris Burns given an address on Orion 1 I know already because I heard it in Manchester. But there were inherent problems with magnetic shielding and noise immunity due to the fact he used current-driven circuits. The end of development and customer deliveries were not in sight late 61, early 62. I did actually see the contract being well known in Ferranti that there was a penalty clause in the Churitz contract. That was the machine to be supplied to Churitz was going to be essentially production machine number 1 of the Orion 1 range. And this meant that if Ferranti didn't really pull its finger out, they could end up giving the machine away and still be in breach of contract. I believe that didn't actually happen. But nevertheless, in fact, legally, my understanding is that was a scenario. From conception in 1958 till early 1962 was already getting on for 4 years. And by the time the machine saw the light of day and rolled out to customers, it turned out to be a 5-year development cycle. That was a long time for a machine, but it's what actually happened. Turning back now to late 61 and early 1962, it was very clear that Ferranti needed a machine compatible instruction-wise and, if possible, system-wise with Orion 1. Clearly, if you were in the legal situation, it had to have a very fast concept to market time, a very short concept to market period, so that in fact, if Orion 1 still was delayed, Orion 2s could be supplied. That actually didn't happen. But I think it was one of the things in the minds of the management at the time, and most certainly some of the engineers like themselves. The machine had to be reproduced without tuning. I mentioned that because, of course, some atlases did involve a certain amount of tuning. So we had a modern machine reproduced without tuning and reliable without scores of field engineer modifications, which is the bane of the field engineers. If you don't get the design right, stable and standardized, the field engineers have a lot of work to do because, of course, they have all sorts of cars with different levels of modifications on them, and they have to modify cars a little bit. So, what Ferranti was seeking was a robust, reliable, maintainable machine, maintainable by the field engineers, using diagnostics and then card swap to minimise the mean time to repair. There were, as I understand it, and again, Ted may wish to say far more about this because he was involved and I wasn't, 2 contenders put to the management, not I leave very openly, but again, and we have the order here this afternoon. Orion 2 based on FP6000 hardware, which then existed and was known to be very reliable, and a machine called a Harriet computer, which again I prefer to leave to Ted. I'm just setting the scene. At that time, there were also resources available in Ferranti. The purchase team in the south of England was immediately available. It was a very good solution looking for a problem, at least that's my understanding. There were premises available because the military division had just moved out of the Hill to Western Road, down the road in Brentnor. And if I'm not stealing his thunder, my understanding is that Ted went to Manchester to see the newly appointed general manager, or Peter Hall, not to us all now, while the proponents of Harrowback were on holiday. So Ted is not only a good engineer and a good scientist, I have to hand it to him, and he wouldn't say this, he's also a good politician. He went at the right moment, he got the green light for what became the 102 project. Right, now what was that project and what did it contain? Well, it is possible to represent a computer as a series of structured layers. And you'll note from what I put at the top of this visual that the whole idea of this is cribbed from the 7-layer open systems interconnection model, which, although not declared as a Ferranti output, was actually produced by Hugh Ross, who I think you'll all know, myself, in 1975, and went into the International Standards Organisation. So I've cribbed the ideas from that. I feel I'm entitled to, since I've had more than handy, and drawn what I think is a representation of the Orion 2 architecture. Not the only possible one, but one which will suffice for our purposes today. Working bottom up, a decision was taken to use diode transistor logic, about which we'll in a minute, random access core store, and a clock which finally ended up at 1 megahertz. But in 1964, I think in the papers the other day, everyone was looking at the possibility of running the detailed cards at 2 megahertz. So a 2 megahertz machine was possible on the cards, but my understanding is it never actually saw the light of day, and I'm open to correction on that. Above that we have the logic design, and again in my computer works article in 1994, I did say that the supremo of the logic design team was the man who designed the adder and the floating point units, because they determined the speed of the machine in the marketplace and its saleability. Well, again, I'm going to say no more about that. We have those today. Above that, we have extra codes and the instruction set. And if I can just, in fact, be light-hearted for a minute, Ferranti, who always advertised themselves as first into the future, were well ahead of the Halifax Building Society. I'm sure you've all seen the Halifax Building Society adverts on television. We give our customers extra. Well, 2 years previously, Ferranti didn't only give its customers instruction codes, it gave its customers extra codes. And we've got Malcolm Big, who is responsible for those, who's got to tell you a little bit about it. Further up the tree, we have all the usual peripherals, mag tape, cards, paper tape, drums, not discs in those days, drums, and of course line printers. The most difficult ones to drive were of course the line printers, because they required heavy currents and quite high speed, otherwise the print would actually cut out. The peripherals have parity, and now moving on from the actual sheer hardware area into, in fact, the interface to the user in the software area. The operating system was OMP, primarily Ordering and Monitoring Program, but Organisation Monitoring Program, there we are. Today we're not specifically not covering that because there is in fact another CCS event, again involving Alan Thompson, planned on that, because it involved also the meanings of time sharing. Above the operating system we have Nebula, and today we have Mark Roach is going to say a few words about that. Nebula was powerful and user-friendly, and a very good programming interface. I had hoped that Stuart Willie, past president of the DCS, was going to come and say a few words about that. He did promise to, but about 10 days ago I spoke to him, and sadly his wife is very unwell at the moment. We are thinking of him, and he's unable to work with this afternoon. On the top of the tree, on top of Nebula, and written in the Nebula language, and using Nebula dialog, we have the user programs, and I'm going to leave the whole of the area to Mark will talk about it. So that's what Orion 2 was as a product. Right, with that acknowledgement to Alan Thompson sitting over here, who spent his whole career with Ferranti and ICL, here is just a listing of some of the features and system configurations of Orion. You'll note that Orion 2 typically had around twice the core store of Orion 1. Don't forget these figures are in fact words, 48-bit words, not bytes, so it's quite a sizable core store. Mag drums, mag tape, and of course line printer and all the rest of it. There were in fact other peripherals available and interfaced, and although not specifically mentioned here, I was looking at the Dell circuit diagram last night, there was in fact a circuit interface to the Atlas peripherals using Atlas logic and logic levels for use when required. So Orion was very, very versatile in terms of machine. Next question anybody with a commercial mind will ask is, where did they go? Well, here is a list again that Northern Thompson is very kind of produced this, of where the Orions went. If we forget the Orion 1s, a bit about which Peter Burns has spoken already, the Orion 2 was the first machine, which in fact was the prototype machine, stayed at Lily Hill House. I don't know what happened to it. Presumably in the end it was broken up when Lily Hill House had to be cleared for other uses. Two of the production machines went to the Prudential Assurance Company. We'll say a little bit more about those then later. Another machine went out to the South African Mutual Life Assurance Society in Cape Town in South Africa. And the last machine went to the Beecham Group Limited in Brentford, UK, where it worked very successfully for a year or two, and was then acquired second-hand by Prudential. And I'm not sure if the Ernest wanted to say something later, but 3 of those machines out of the 4 made and sold commercially were acquired by Prudential and became their workhorse from 1964 to 1976. Okay, well that's a quick overview of the project, how it happened, and where the project in fact went to when it was sold commercially. Now, as Roger said when he introduced me, my job, well, my official title was Post-Design Development Engineer. At least it was, as far as I remember. Miss Gordon Harvey, who's here today, told me to the contrary. And my job was in fact to redesign circuits that did not work during development within the shortest possible time. So I looked at most of the circuits and was prepared to do whatever was required when modifications or redevelopment was required. As far as the Orion 2 is concerned, before I was involved, there was a decision to use no logic. This uses one type of gate. I'll give you a circuit diagram for a couple of seconds in a minute. This in fact uses one type of gate that does everything with appropriate logic design, designed operations, OR operations, NAND and NOR. From an engineering point of view, it's a very clever and elegant form of logic because it standardizes everything on one circuit type. I understand, and again, I've not talked to the gentleman concerned, but others have, and Ted may say something about this, that it was derived from earlier Griblons, which were in fact a form of diode transistor logic. The earlier Griblon ideas, produced by Maurice Gribble, also Francis, most of you will know, went out to Francis Packard to Toronto. They engineered the ideas into hardware, and by the time we saw the engineered version, the cards actually came back to us at Lily Hill as ready-to-use cards to go into the machine bays as the logic design was implemented. There was no mandatory development, at least to get the basic logic going, because the 701 cards, which these cards were called, ran at the moment to put them in the base. They used germanium junction transistors, which at that time was state-of-the-art, around 1961, early 62. Somebody may ask the question, why in fact did he use silicon transistors? Well, the answer is we did, and the process of silicon conversion took place in the UK at Lily Hill early in 1994. Sorry, correction, 1964. I knew I'd missed you when I did that slide. Thanks for that. This really, because he used germanium transistor, I must make a comparison with Atlas. Most of you know that Atlas used point contact germanium transistors, known as OC170s. Somebody say something. OC170s. Yes, they were junction, were they? Also, OC170s were point contact. Well, we'll leave it anyway. OC170s were, I think we'll say, they were very early version transistors, right? My understanding is that Mollards made OC170s, tested all their production, and the highest performing transistors went to Franklin use Atlas. Right? We'll not argue the point about whether they were junction point contact. I wasn't used to do a point contact. Ted, as I say, I did. But Roger, you told science.
Junction transistor.
They were. Well, anyway.
I've got the catalogue at home, I'll check. I'm a lot of catalogue.
The point I'm making is there's quite a little bit of selection and tuning done of the transistors that went into Atlas, as I understand it. And that had to be overcome. It was. We used totally standard transistors right across the line. So that was the point I was trying to make. Okay. We want to get out of selection and that goes with it. I just mentioned the 701 card, the basic logic in Orion 2, nothing unusual about this. 3 diode inputs, standard diodes, straight into the base of a transistor, which was quite rugged, right? Where these in fact went up, the collector went down and vice versa. A very straightforward switching circuit that worked day in, day out, night in, night out, and did its job. I don't really think there's much more to say about it actually. There were 6 of these gates packed on what was known as a 700 series card, which was about 6 inches by about 4 or 5 inches, which in fact were also the same cards that went into the later ICL 1900 machines. But they're a good piece of engineering, and the sign of any good piece of engineering is that once you've done it, you never hear about it. And that really is that really was the case with the 701 circuits. I think it's very desirable, and I'm sort of treading careful now because I don't want to say Chris Berman sitting in the corner, but anyway, to just say a little bit about Orion 2 circuits and compare with Orion 1s. The Orion 2 clock was about 1 megahertz, Orion 1 was about 500 kilohertz, at least based on the information I have. And as I said earlier, in 1994, 2 megahertz clock was being investigated. 1964. I've had enough time, haven't I? 1964, 2 megahertz was being investigated. On the issue of noise immunity, the Orion 2 circuits were non-linear. You either got a complete digit driving the circuit and it triggered, or you got part of a digit, it wouldn't trigger. There was very considerable noise immunity from the non-linear nature of the circuits. So there was a dead band for noise within around 70% of the middle band of a digit. In other words, the middle section of the digit between 0 and 1. In contrast, and I thought my way through this, and again, I value reiterating the comments that people ought to make, the Orion 1 circuits were linear, and in fact, they could, if the opportunity arose, tend to integrate magnetic noise from any source from which it should not have come. So the Orion 2 had voltage-driven, lower current circuits, because you didn't need an awful lot of current in the basic logic circuits. And think about parasitic inductances, which are an absolute nuisance on computer cards, which integrate noise, were either eliminated or minimized by virtue of the lower currents which were coming back. Okay, now I want to put my reputation on the line and give you a case history of one particular card that became my job to redesign. Well into the development, David H. Smith, known as David Hesitation Smith, because he dealt with hesitation, cycle steam and interrupts in the logic, came to me and said he needed, in fact, a new cable driver circuit to drive the cables, particularly with the line printer. So I got the job of totally designing from scratch, like yesterday, as I mentioned on here, a cable driver circuit which would in fact produce current pulses with very fast edges, particularly to design the line printer. The solution I adopted is known as a Darlington pair. Now before, this has got a male audience, before everyone's mind goes off in their own direction, a Darlington pair is not the pride and joy of every young lady from that county Durham town. So forget that. What a Darlington pair is PNP-NPN transistor pair, complementary transistor pair, in which an input signal turns one transistor on and the other transistor off. Well, this is quite a neat solution to the problem I had to face. If you put something like 100 milliamps steady state current down this chain, you apply a driving pulse from the driving logic. This transistor will turn on to say 200 milliamps. This one will turn off. Then you end up with a 200 milliamp pulse, in fact, going out on the output between the two transistors. And in fact, it's a very fast pulse. As one turns on, one turns off, and bang, off it goes. Very interesting circuit. Did the job. My job initially was to breadboard it. Breadboarding means you in fact put together a hookup, usually in those days on a piece of ferro board, with the right transistors, plug it into the machine and make sure it works. I did that. I did the calculations of the current quite accurately and the voltages. The car was all set to do the job it had to do, but sadly, being me in a hurry, I did the power calculation on the back of an envelope and got it wrong. So when I put the breadboard circuit into the machine, there was one almighty bang, I can still remember it now. A cloud of blue smoke. Jack Templeton, who was Corbett's second in command in hardware, said, very patient, you're very patient with young engineers like me. I think you got it wrong this time, go and have another go. Within 24 hours I got it right, and we got the card right. The final 787 card had 38 transistors on a 700 series card about this 5 bits. It was one hell of a job to make because these were in 2 stacks on the card. You couldn't otherwise get them on. And many years later, I met a man called Gordon Calverley, who many of you will remember as the procurement man from West Gordon, who said, in 1964 I had a car that was a devil of a job to get made. It had 2 stacks of transistors on it, in 2 layers. At that point I kept quiet. So there we are. I've introduced now, I think, what Orion was as a product. Said something about the politics that got it going, and I'm sure that Ted, if he so wishes, will say whatever he wishes to say about that. So I think it's now my pleasure to introduce Ted, who was, I think, in many ways the godfather of the entire Orion project. He was one of the working party which got it off the ground. Perhaps I can sum up Ted, if I'm being reasonably polite, by saying that he got his brain into gear by doing a tripos at Cambridge, 2 parts in maths and 1 part in theoretical physics. And then when he got his brain into gear, he joined for Anti and really got it moving even faster. What he did is what he's about to tell us now. Ted, over to you.
Hello. Yeah, I'm there. If anybody wants to make comments or correct me of what I'm saying, please do, because it might be interesting. Very well. And I'm going to... how many people were here at the meeting in February on Orion 1? Oh, about 50%. I was going to repeat a bit about the reasons for the general architecture. If you can put up with a bit of repetition for those who weren't there.
Yes, please.
Okay. And as Mark said, Frank said it, in June '58, Brian Pollard appointed 3 of us to produce a proposal for a medium-sized scientific and commercial computer, which was to use neuron circuits. And this would be the main money-making Ferranti machine for the next 5 years, the other machine being Atlas, which was not expected to be high volume. And there was a worry whether one could, in fact, combine a scientific and commercial machine into one and still be competitive in either market. But Ferrantis were strong in the scientific market and wanted to remain in it, and clearly had to go for the commercial market as well, and there was not the capacity to do 2 machines at the same time. So in a sense there was not much choice about doing that. But on the other hand, that would not have justified making a machine that was not saleable to anyone. I do not remember discussing this problem with others much or at all, actually, or it bothering me. But also, if I don't remember something, it doesn't mean it didn't happen, because I have been continuously astonished at the things I spent a month on, which I've completely forgotten I ever spent any time on at all. Does anybody else have that problem? Yes. But I hope that the things which I think I do remember are more reliable. I haven't got much good evidence about that either. Anyway, we were aware that this machine was not a minimal machine, and the Hariak machine, which will be coming into the story later on, 3 years later, was an attempt to fill in that lower end of the commercial market. The other two people on the planning were Ken Johnson and Charles Lindsay, but they neither had anything to do with computer architecture, nor were they particularly interested. So they and I more or less went our own ways. I've been a programmer for a year and a logic designer for 4 years, mainly on Pegasus CPU and on magnetic tape, as well as doing some architecture jobs. And on this Orion planning, I talked to everybody, software people, George Felton, John Davis and Derek Millage, and I talked to the salesmen, and I talked to all the various engineering branches involved in computers. So I just acted as a collector of ideas, and an idea or two of my own, and turning it into a coherent proposal, I hope. From the beginning, I did intend the proposal to include time sharing, now called multi-programming. It was much talked about in those days in the journals, along with other things such as interleaving, but there was never any discussion of the details of implementing it. But its possibilities were so mouth-watering that I imagined everyone would be putting it in, and it was a great surprise to me to discover years later that how few people actually did in a full-hearted way. We've been doing a lot of discussion of time sharing with a view to another meeting Alan Thompson is organising. And
could I say that Orion 1 included all that? And Orion 1 included running lots of programs at once.
oh, it's the same. Orion 2, Orion 1, we're talking about the planning of Orion 1
Sorry,
now.
I missed the point. Thank you.
Orion 2, even more strongly than what Frank said, it was designed to be absolutely compatible. That was one of Malcolm Big's job, was to make sure that any program which would run on Orion 1 would run, without any question, on Orion 2. And that was quite a job, wasn't it? But in the discussions, emails have been passing back and forth between a number of us about the early history of time sharing, which there's going to be another meeting here about one day. But there were various people suggested the idea, and it was in the journals, I think, all the time. And I think Christopher Strachey gave a talk, Stanley Gill gave a talk, other people may have, but I think I heard about it, because I certainly didn't go to the lectures where they gave the talks. I came across it in various journal references, especially, I think, in one issue of the IBM Journal of Research and Development. So that's, but as I say, nobody, I came across nothing which suggested the details of how one should do it. And I've got a little quote, if I can find it, from, yes, this is just a little, this is from 5th of December 58, at the end of the battle to get rid of neurons in Orion 1, having failed. I think, yes, that's the right memo. Interrupt and time sharing, I say. This is a memo to Brian Pollard on the 5th of December 58, just before he resigned or was fired, whichever you prefer. And I said, so far as I'm concerned, on interrupt and time sharing arrangements, I feel the need for hard thought to arrive at a cheap, comprehensive and snagless set of facilities for interrupt and time sharing. This must include a detailed understanding of all the types of applications we can think of. It is the next subject I propose to think about. So that was the situation. Nobody talked about how to do it. Yes, well then, now coming on to the details of the Orion spec, one of the first things one has to decide on in designing a computer is the word length, and in our case, the character length. I've talked to George Felton over the years since, and we would both have loved to have 8-bit characters rather than the 6 bits we actually had, but we didn't dare because of the extra memory required to store character data. And bear in mind, we were already worried about whether a machine for combined scientific and commercial use could be competitive in either field anyway, so there was a big concern about the size of the machine. Yes, we didn't dare. And this is an example of where one has to remember that, blissful as it would be to design a machine of the future, it's no good if it's too expensive to sell now. We didn't know that we should have 8-bit characters, that it would come one day. Actually, the most compelling reason to me for keeping a 6-bit character was not even what I just said, but it was this. A word, I said, must have a power of 2 number of characters. So with a 6-bit character, one could have a word length of 48 bits, which is good for floating point, and it's 8 characters. But with an 8-bit character, one can have 32-bit word or 64-bit, and 32 is too short for floating point, and 64 is longer than necessary, and adds a lot of expense to the parallel arithmetic unit. So that was a strong reason, as well as the waste of space having an 8-bit character instead of 6-bit. In February, when I mentioned this, George suggested, well, what about Pegasus, in which we had 6.5 characters to a word, and well, my argument, I think, I forget what it was then, it's same as now, that we were very keen on elegance and cleanness of specification of instructions and so on from the programmer's point of view. And I would have been terribly, I can't imagine being happy with anything other than a power of 2 number of characters to a word. I don't think I could dare. And it's interesting that I really can't think of a computer since then that hasn't kept to the same thing. I mean, 24-bit computers, 6-bit characters, and 32, 12, but with 8-bit characters, 16-bit, 32 or 64-bit words. Does anybody, can they offhand think of another computer which didn't stick to that since those days? No. It's surprising, really. Oh, and yes, we assumed from the beginning that the machine would be parallel. This seemed essential in order to be competitive and to match the performance of core stores. There was a memo from Chris Wilson around that time saying what speed he thought scientific machines needed to have in order to be competitive, which I've only got a reference to it, not what it actually said, but I would imagine that it certainly ruled out serial machine anyway, and it probably ruled out Orion 1, but I'm not quite sure. I know you think that, George, because you said something like that to Peter Hall once in about 1961, didn't you? You said, what change would you like, George, to most of all to Orion? And you said, for it to be 5 times as fast.
And he said, thank you very much.
That was shortly before the start of Orion 2, wasn't it? Then one has to decide on the instruction format. We rejected a 24-bit instruction, such as the 1900 series has, as being too cramped. And so we settled on a 48-bit instruction, and this allowed a nice, comfortable address length and also replacement and modification bits. So it made a very nice instruction, I think. memos and notes about discussions exactly at what address length to have, right until early 1959. So we were thinking about it at quite a late stage because they were already getting quite detailed logic design done by then on the basis of a 48-bit parallel arithmetic unit. But what I've said here is I presume we were aware that with time sharing, programs would be operating from different places in the core store on different occasions, and that would have affected, well, the ways of handling addresses. At any rate, either you'd add the starting point of this particular program's core store to each address or something like that. But I haven't got any notes about that. The Pegasus type of order code was our starting point, to which were added floating point and field handling instructions and many other improvements, these being mainly specified by George Felton and his programmers. And as, who was it, Jeff Nuttall?
John Thompson.
Oh no, somebody said at the February meeting, somebody sitting back there said, why did you have the most extravagant set of instructions in Orion that's ever been seen in any computer, I think is what he said. Jeff Newell, was it Greek?
No,
Not Jeff Strauss. Sounds like Jeff Newell. Well, which the answer is, George had given the answer to me before, which is that when I got shoved off the project after the neuron battle, Charles Lindsay was responsible for the details of the engineering. And instead, well, what he did was, whenever George and his people came up with another idea for some nice instructions, he would regard it as a challenge to see if he could do it, and so he stuck them all in, more or less. Whereas the engineer's job in that situation is to cool the ardor of the programmers, because and the reason that my favourite tag, or little saying to myself, all when I was designing computers, was always, if in doubt, leave it out, because it's always so tempting to put things in, and you can always argue in a very vague way that the total performance, the bang per buck of a complete system, is going to be much improved by every little addition you do. It's going to be worth several times as much on the bang per buck as it costs in the total buck. So if one didn't care about the price of the computer, one would add all those things in. But of course one has to care totally about the price.
The bulk.
So, yeah. Right, well, that's enough of that for the moment. I'll come back to I was going to tell you this detailed story of the battle to get rid of neurons for Orion 1, involving an attempt to overthrow, the only revolution I've ever been involved in, an attempt to overthrow Brian Pollard as manager of the computer department. It's a story of incompetence. I mean, the three of us, Hugh Dovenall, not here today, and Harold Marchant and I, were hopeless revolutionaries. We started, at least we did decide to have one, which was something, but I'll tell you later on. Now, I'll change the subject to a bit of logic. I'll just tell you some of the logic from the mill, things to do with the mill, actually. Right. That's right, yeah. How many of you are familiar with old-fashioned computer logic diagrams? Well, how many of you aren't, on the other hand? Well, not many. Well, that's what I have to put up with it. But I think well, this at least isn't. This is just a picture of the biggest registers. This shows the general organisation of the Orion parallel unit. We've got 4 48-bit registers there, which are flip-flops. The general way an instruction is obeyed is, after having got the instruction out and prepared it, modified and replaced, and now you're ready to obey it, So, can you still hear me? Yeah. Right, so you've got, you go to the memory to get out. Then you have the clock time when it goes through the mill and back into one of those registers, having had whatever was needed done to it. And then you have another, and then you send it back to memory. So this gives an idea of how many roots. Each of the 48-bit roots has 48 NORs, of course, to operate it. You'll see that in more detail on the next picture. I don't know who did this schematic. There's no signature on the original drawing, which I have, but it's not very good, but because, my friend is, because, I mean, look at this. Take that, for instance. Really, one could do better to represent that by one line, and thus, sort of say, 0 to 5, stroke 0 to 47, stroke 0, to indicate that sometimes you use the whole 48-bit bus and sometimes you don't. It's misleading, I think, to say that. I don't know to blame. Also, there's a deliberate mistake in it, because I'm sure that's in, because for subtraction, the way we did subtraction was the inverse of a register into the mill and force a carry into the bottom. The mill itself didn't do subtraction, it just did add and logical operations. So, and as you see, it would do, yes, it would do or and equivalent and addition. And maybe that means plus, yeah, it seems to have left out or. I'm sure that must mean plus. And then you could have shifts on the way in and shifts as described on the way out. And this is to do times 2 is for multiply, which I think was by then a standard way of doing multiplication in half the number of iterations one would otherwise needed. The simple way to do it is to add the multiplicand in, if the multiplier, working with the multiplier bits from the bottom up, and if the bit is 1, you add next multiplier bit. But you can do it in half the number of iterations. You take 2 bits at a time, and that will say that you have to add either 0, 1, 2, or 3 for the 2 bits. And that's all right for 0, 1, or 2, but 3 you would have to add in 2 places, which you can't do. And so the way you do that is to carry a +1 into the next iteration, which is, let's say, a carry into the next iteration, and subtract 1 on this iteration. And so you only have 1 addition to do. And this times 2 was if when you needed to add twice the multiplicand. And these things here, there's something about, I think they're shifting down 2, that's because the multiplicand and multiplicand and the partial product being formed are going to be partial products accumulating here. They both get shifted down 2 places each time. So, I think that's right. So in the end, you get the full product there in B and C. And does anybody recall what D was for? Because I haven't been able, I haven't gone through all my data, but I really don't know.
Data? Is it data?
Not, I shouldn't think so. Well, it's 40, yeah. No, I was afraid nobody would tell me, yeah.
Oh, cable drivers.
Yeah, well, for some reason it was useful. I mean, we could have said, yeah, but then hesitations didn't come into the mill. Hesitation sent the word to the core memory. It took a core memory, if I remember rightly, cycle away from the central processor. Anyway, well, I thought somebody might know. Next, I think that's all I have to say about that picture. I won't say much about this one, because this just shows the other short X, Y, Z, and oh, F was on the previous one. Oh, then let me just D. E was we used for counting the number of iterations, that's all, in multiply and divide, and possibly shifts. So let's see what's happening. F's got lost. There was an F in this picture for the function. X, Y, and Z are the address bits of the instruction. J and W, U, V, and T. I was going to ask whether anybody remembers what they were for. Anyway, we needed them for.
J is the current address, W is the abandoned address.
Ah, I see. Of course, yes. J was the current, right? Yeah.
W is the address you abandon. The instruction has to be abandoned. That's the address you go back to.
Ah.
So it's a string of 116 or.
Oh yes, I see. Because it might not be the same address as that. Thank you. Right.
It wasn't updated during action.
Well.
It wasn't updated during action.
Ah. No. Right. Yeah, this is just to show, well, mostly to show how many logic elements there are in a clock time, because 1 megacycle, as you know, for ordinary operations. What I really want to show here is that how simple and how little the logic is to do a 48-bit carry with only 4 extra logic levels. With the way we did it, there are 8 logic levels, the longest path for a non-carry process from register back into register, and that took a microsecond. And for full carry propagation, it's 4 extra logic levels, and the clock has plus. I see in my documentation that the clock there was for a carry operation was 1.2 microseconds, so it's only 50 nanoseconds per, 50 nanoseconds per extra NOR gate. But for an ordinary sequence of events, we have, there's the flip-flop registers. One of them is selected by a NOT control. This being NOR logic, if you want something to go out onto the bus, you make the control 0, unlike for AND logic, because since these are NOR logic takes all these together and inverts them. So if you want to kill anything getting through, you make the control a 1, and then you guarantee that NOR gate has a 0 output. But if you want to let the number through, you have to make the control 0, and then whatever the contents of the register is gets out on the bus. And of course you can tie all these outputs together, and they're ordered together, so you get whichever register you want onto the input buses to the mill. So we've got, because there's a flip-flop which is set in advance every digit time to control which register is to be allowed onto the buses. That's to save a lot of time. When you have to set that in advance, it would be a long waste of time before you even got the stuff into the mill. But because it has to drive 48 NORs, it needs some power NORing. So there's one more logic level here just to power up the output of the control flip-flop. And so we've got 1 level for there, 2. And then we've got through the mill, 3, 4, 5, 6, and then this is gone off the picture, but goes in here. This is the mill output called S sum is one of the inputs onto the bus into the registers, and let's say it's that one. And our flip-flops needed an input on both sides, opposite inputs. So we have another 2 levels, so that makes 8 levels altogether. That was just an ordinary standard non-carry digit time. And maximum for the full 48-bit propagated carry is another 4. So, which is, I was surprised, but where I heard about it from was an article perhaps around 56, 57 in a journal from the National Bureau of Standards, which described this fact. You really don't, it doesn't need much logic, and it doesn't need many stages of logic delay in order to do carry the 48 or whatever the length of things is. Before that, people had made a big fuss about doing parallel carries. It seemed to me, well, that was my impression. I could go into this in more detail, but it's not. I will just say 1 or 2 words. The way we always put an N before it. We named signals, hopefully, so that it would be easy to understand what they did. And a name like N means, N always meant that it was 0 for when it was, what it said was true. So in this case, this means, this is bit 0 of the mill, and this says not transmit on bit 0. Transmit is the condition for transmit a carry, that is to say, is that there should be at least 1 of the 2 inputs to that bit should be a 1. So in other words, logically it's not L0 or K0. That's not quite true because it's, transmit is actually only 1 or other of the inputs, but not both. And it didn't matter in this case, it worked anyway. And then G0 means not generate a carry in bit 0, and that's the inverse of it, and logically it equals L0 dot K0, and then combining that we get, this is the L0 not equivalent to K0, that going into it, and then we bring in previous carries from lower down into the picture. And that's the path. If there's not a carry, which lets that through, and if there is a carry, if there is a carry, this is allowed through, and if there's no carry, then these are all zeros, so this is allowed through onto the subject. It's not very complicated. So that's the basic mill without a carry. So when I come, that is just to set the scene for the carry.
Raise it up a bit.
Sorry?
Lift it up.
Oh, yes, sorry, yeah.
Protect us in a way.
Quite right, yeah. That's better, yeah. Right, well, for the purposes of fast carry, we divided the 48-bit unit into 12 blocks of 4 bits. And for each of those blocks, within the block, we generate, once if a carry came into that block, we had enough logic to do all 4 bits at the same speed as it did in bit 0, which took about an average of 3.5 NOR gates per bit position. Not a huge penalty, and it compared with what we had before for the whole arithmetic unit. Then, that's within the blocks, but then we generated the signals for each block of 4 bits. We generated a signal saying there's carry into that bit. And we did that by, first of all, with each block we generated 2 signals, one saying this block of 4 bits generates a carry, and another signal saying this block will transmit a carry across it if a carry comes in. And the condition for that is, the condition for generating a carry is either there's a carry in, this is for block 0, either there's a carry into, if generated in position 0, L0.K0, and it's transmitted across L1 or K1, transmitted across L2 or K2, and L3 or K3. That's for a carry generated in position 0, or it might be generated in position 1, and then it has to be transmitted across position 2 and 3, plus the same thing for positions 2 and 3. So it's quite simple, and the logic to do that is here, which is that first equation is done by this. As you see, we want to AND these things together, so we have N of all the signals concerned, tie all the outputs together, which is an OR, and then that signal is generate a carry from block 0, and that's its inverse, which we will need. And for transmit, it's even simpler. The condition is simply that there's a transmit across all 4 positions, or, yeah, as it says. And the logic to do that is just that. Same idea. So now we've got a signal from each block saying if carries to be generated in it and if carries to be transmitted across it. And we use that to generate a carry into each, a signal saying there's a carry into each block. And the idea is simple. There's a deliberate mistake in this, by the way, I ask you to spot. I'd be interested if anybody, I hope somebody sees it. But anyway, there's a carry into block 1, if there's a carry into block 0, and it's transmitted across block 0. That's a mistake. That's the mistake, by the way, yeah. And the other reason that there might be a carry into block 1 is that there's a carry generated in block 0. So that's the logic equation, and that's the logic elements, just 2, same idea as before. And for block 2, it's just the same, except it has to go across, it's a bit more complicated because it may, because there's one more block it might have to go across. So that's the condition, generate, carry into block 0, transmit across these block 0, transmit across block 1. Or generate in block 0, transmit across block 1, or generate in block 1. And that's the logic for that. And that would only be 2 extra logic levels. It's not obvious, but if one follows out the maximum chain, compared with the non-carry operation, one would, if one did this for all the blocks up to block 11, then one would only have 2 more logic levels for a full 48-bit carry, whereas in fact we chose to have 4, because, I imagine because of loading problems, but I'm not sure. And so what we did, using 2 more levels, was generate a carry into block 4, like this, but then that carry into block 4 was used in block 5, 6, and 7, in the same way as carry into block 0 was used here, but it needed, that means that the signal that you were using into block 4 as the carry into block 4 was had 2 more NOR levels in its worst case string than the others.
Can I ask a question here?
Yes.
Did this carry on into the West Gorton 1900s exactly the same?
I don't know, but it was. I think I would say it was well known.
Yeah.
I'll tell you who did the. I should tribute some of the people who did things. It's Glyn Emery, with the help of David M. Smith. David M. Smith did all this.
Right.
For the
Well,
mill.
it was exactly the same as used in 24-bit word in the Stevenage 1900s. And then later on we had to turn that into TTL and do it all over again, exactly the same.
The same kind of fast carrying.
Exactly the same, except for only 24-bit version.
Yeah, yeah,
With
sure.
block carriers, or
Yeah.
look-ahead carriers, we called it in those
Yeah,
days.
carry
And
Carry
eventually,
look ahead.
look ahead.
yeah,
Why is it called look ahead?
Well, because you take a block of digits, you process the carry situation for that block,
Yeah.
pass it on to the next.
Quickly, yes, with just a, yeah, right, yeah.
So it becomes well maintained.
It was already, as I say, I heard about it in 56 or 57, and Glyn said that he heard about it from somebody else in Ferenti, Bracknell, I think Peter Niblett, and I think and I don't know where he got it from, presumably because it was fairly well known by then.
I know in 75 we bought it on chip.
I'm sure. Well, yeah, well, for a whole 20, you mean the whole adder, 24 minutes?
Well, no, we still had the sections.
All right.
4-bit adders, but we had the look-ahead chip as well to go with it.
You mean a special look-ahead chip?
No, it was, by then it would become a chip.
What? How much was on that chip, the look-ahead chip?
The chip that you put on those last two.
All those things about, yeah, all the special
Yes.
block generate and transmit. Yeah, I see. Yeah. Yes. Well, yes, what did I know? Yes, that is the little thing here I was going to say. Was that this gives just an idea of how many NORs there were per bit in the arithmetic unit. In the middle there were 8, without special stuff for carry, plus, and that was without shifts, plus 7 for the different sorts of shifts. And then the inputs and outputs to the registers, 8, and the carry within a block, to fast carry within each block, 4, 3.5, and the block carry and generate stuff altogether only took about one average of about 1 NOR per bit. So it's very small, as well as being quick. Yeah, that's what I wanted to say there. Yes, I suppose I'm not surprised to hear that I'm sure everybody did it after that. It must have been in the 1900. You say what was? Yeah. Right. How am I doing on time? Not fine, am I? How many?
A few more minutes.
Few more minutes, right. Okay, so I'll now do the story about the revolution, or the attempt to get rid of neurons in the first. And in the middle of this, I'll read you part of a letter from Peter Hall, an email which he sent a couple of days ago, giving the situation from his point of view at that time. Yeah, right, and yes. So as I said, Hugh Devonlord, Harold Marchant, for those of you who knew them, and myself had been up for a last attempt to persuade Brian Pollard. We'd given up on Gordon Scarrett being persuadable about anything at that point, so we were working on Brian Pollard. And I was a friend, I liked Gordon Scarrett, but along with most people, we regarded him as a clever man, but a technological disaster, I think. Well, yeah, and I know. Anyway, this is the story of 3 hopeless revolutionaries failing to succeed. Now, how much shall I explain? You know that there was the North and the South in Ferenti's computer department, and they didn't get on that well together. Most particularly, Brian Pollard didn't want to know anything about sales and programmers. Yes, the Manchester management's attitude to customers seemed odd to us Southerners. It seemed that we should produce a computer, it seemed to us that they thought we should produce a computer that we thought was good, and then present it to potential customers to take it or leave it, rather than doing a bit of market research to see what people wanted. And it was clear to us that neurons were not the circuits to use, for several reasons. Yeah, well, I won't go into. And that there were an excellent alternative available within Brandy, the Grimlons. Yes, we tried, as I say, yes, we tried to persuade. Actually, Bernard Swan and I think George Felton came up I remember one meeting, we all went up together to talk to Brian Pollard to try to persuade him to dump Scarrett's neurons, and we failed, didn't we? That was probably September 58. And then, so Harold and Hugh and myself, I'm not sure why Harold and Hugh were involved, because it doesn't, anyway, but never mind. They had same opinion about it. We were up to have a last go at Brian Pollard, who, I must say, I have to say, he was very tolerant of us badgering him. And looking at some of my notes I wrote at the time, it was very sort of difficult young man. And wouldn't shut up. And I had lots of pertinent criticisms of his way around the department. I don't know whether I told him anymore. Anyway, he was very good-natured about it. So Hugh and Harold and I went up and had a last attempt and failed on November the 5th, 1958. And so we came back on the train afterwards, and fireworks were going off, of course, all on either side of the train, and we resolved that we should have a revolution. And send a telegram, the form of it would be send a telegram to Sebastian de Ferranti, who was now managing director, saying we wanted to discuss the question with him. And we weren't happy with Pollard's decision, which we were sure was going to lead to a failed machine. And we also made a vow to each other that we would never shave again, and the forfeit was that anybody who did shave should buy 8 pints for each of the others. And then the next thing that happened is that, well, 2 things happened really. Bernard Swan had a word with Hugh, I think, saying it wouldn't look very good, because we had sent the telegram, and Bernard obviously knew we were going to have a meeting with Sebastian, but he said to Hugh, it wouldn't look very good if you've got 3 of you with 1-week-old beards at this meeting. And so Harold's face was too short, and his didn't look good, and Hugh's grew in some patches and didn't look good. So they both took them off, and I was allowed to keep mine, which is dates from November the 5th, 58. I don't think I got many of them. I don't know. I should have insisted, shouldn't I? But, yes. Right. So that is fine. But then, so far, we're not very far with the revolution, but then we decided to send this telegram, and we left Hugh to do it on his own. It's something so important, we should have all written out and talked about together. And whatever is said in it, Hugh can't find it, never has found it. We have no idea what was in that thing, but we do know that Sebastian didn't understand what we were getting at. and he had a meeting with us, but to our astonishment, when we went into it, it wasn't Brian Pollard who was there, it was Peter Dorey and this property manager, Humber, in the south of England. Which, we were really very incompetent. Incompetence number 1 is we didn't draw up the document very carefully ourselves and discuss it. Incompetence number 2 is when we got to this meeting and it was unlike that. And then Sebastian obviously had decided to take the line that he didn't want to fire us, so he wasn't even going to get onto whatever it was we wanted to talk about. Just all the volumes. And we were stupid enough not to say, well, do you know what it is we wanted to complain about? None of us sent out. So we finished the meeting, no further forward, except that Peter Dorey decided to get rid of us from Lily Hill as soon as possible, which he did within the next few months. So, yeah, hopeless. And then, of course, the next thing that happened was just before Christmas, I think, Pollard, I know he made some impossible demands to Sebastian, which were turned down, and he felt either he would have been fired or he resigned or whatever. Anyway, he left, and Peter Hall then took over. And we stupidly I mean, having seen, we didn't, we didn't know. I mean, we could have deduced that Sebastian didn't know what it was we wanted to talk about, I would have thought, but we didn't say, well, in that case, Peter Hall probably doesn't know about this neuron battle. And he didn't. He said to me a few days ago that he didn't know about it. So, but what happened when he took over us, we were waiting for weeks, waiting daily, hoping for a message from Peter Hall saying, come up to Manchester and tell me what your complaint with neurons was. But it never came, and we never sent a message to him saying, don't you know about the battle to get rid of neurons or whatever? So that's the third appalling word. So at this point, I think we can have Peter Hall's little note about what it was like for him. Yes, so he said this a couple of days ago. The Ferranti computer department, I took it over in strange circumstances. Brian Pollard and Bill Elliott had both left under a cloud. I was asked to take over the department for what reasons I know not. I had absolutely no knowledge or understanding of computers or what they did. But it seemed I had a reputation for rescuing ailing departments, false, quite a lot of experience in maintaining large R&D departments, managing large R&D departments, and my background was pulse circuits and the development of semiconductor devices, that was at Withenshaw. I found that an important gang had left to go with Bill, and the warring factions were at me to develop what became Orion 1 and Atlas. Lily Hill seemed to be fine, I let them get on very well. And he also said that one of the first things that happened when he took over as Peter Dorey dashed up to Manchester and put it to Peter Hall that he, Peter Dorey, should be made the complete manager of Ferranti Bracknell, which Peter Hall did. He seemed to be a suitable person. Now, yes. So everything seemed to be going on fine in Lily Hill, finishing off Perseus. So what was he to do with the situation in Manchester? I could have done with some of Arthur Humphrey's more hindsight sooner, in quotes. Gordon Scarrett had very good credentials, and he convinced me that Orion would work. If only I'd listened to my old friends and colleagues at Withenshaw who had advised him not to use neurons, incidentally. And then you lot came along to rescue me, but nearly 3 years later. Then if we had an Orion 1 made on Briblons, he said, I'm sure we would have seen off the big competitor, which was Leo 3, which had time sharing because of George Felton told them all the details of it on January the 14th, 1960, wasn't it? And they did very well. They sold, apparently, somewhere in Australia, they sold over 50 Leo 3s. Over, maybe 100, I don't know. Anyway. So that's the one little tiny last bit, which is the start of Orion 2. Yeah. Which is, I fill out on what Frank said. I knew that, well, two things happened. One, my girlfriend, because I wouldn't marry her, she went off to Canada, Audrey Williams, as she was then, and July, and I hadn't got that much to do in the summer, so I started thinking about a gribblized version of Orion again, and I knew that Orion 1 was in big trouble. So I sent Peter Hall a letter, putting the possibilities using faster circuits. I think I had Atlas in mind, we were persuaded not to. Oh, well, other people were persuaded not to, like Gordon Harvey later on, that they were too tricky a circuit to use on a really reliable ordinary computer. Anyway, so I sent this memo, and then I was astonished when he asked me to come up the next day and explain in more detail what I had in mind. And I did that, and I was even more astonished when the day after that, he set the whole Bracknell logic design group, which was just coming to the end of Perseus, to work on it in a few days' time. And what I didn't know was that the crew was threatening to cancel their Orion order, which might have escalated to all the others. And so he was, that's why he was in such a hoped and succeeded in persuading them not to cancel the order by offering them a machine 5 times faster in 3 years or whatever length of time. Frank mentioned the Harriac earlier on. Harry Johnson had always hankered after a 24-bit, very simple, purely commercial machine. Fair enough for his market. And he and Peter Hunt and Bernard Swan had been plotting this secretly for a while. And in fact, they'd all gone on holiday at this very time in September when I sent my note to Peter Hall. And I didn't know about it because they'd done it secretly. And so they came back from holiday, all 3 of them, to discover that everything had been preempted. But Orion 2 was being done and there was no change. And what's more, I'd been working on Nebula, which Peter Hunt was in charge of, so, and I'd left that too, so he wasn't very pleased. But so that's how Orion 2 started. And I said to Harry, well, it's your fault that happened because plotting secretly without the knowledge of the manager. And his comment was, well, it's the manager's business to know what's going on in his department. I think that'll be enough.
Thanks, Ted.
Thank you.
There was, in fact, for me personally, a silver lining to some of the things Ted has mentioned. Whether or not the Gordon Harvey's here with us today.
Microphone.
I moved down to Bracknell.
Microphone.
You want to use the microphone? Ted,
Microphone!
Oh, sorry. Yes, I see. You're a microphone.
It's being recorded for posterity.
I was just saying there was a silver lining for me personally, came out of all that Ted described just then, at the end of all the politicking. I moved down to Bracknell as one of 2 research staff with Gordon Scout in August 1962, not realising that Gordon's career at that time was in a downward spiral, as Ted has described. When I did realise, I very quietly had a word with Gordon Harvey, who's here today, and got myself quietly transferred into the Orion team, which is, I think, the best thing I ever did. Okay, you've heard what Ted had to say about his part in Orion. It's now our pleasure to introduce our next speaker. There were just 2 of us in the early Orion team from the north of England, or joined from the north of England. I was one. The other one was Malcolm, who's about to speak to us now. He joined the team straight after completing his PhD in Manchester, notwithstanding the fact he's not a northerner. And as I said earlier, got to work adding a little extra to the instruction code, 40 years ahead of what the Halifax now publicised today. So, Malcolm, over to you.
Yes, I'm not a northerner. I was only at Manchester, at the university there. Nobody's gone to Watford before us.
We are a lot of amateurs.
Switch it off with the chair,
Right, make sure I can put things the right way up. Yep. That is right now. Well, a bit of background history as far as I'm concerned, because just to correct what Frank said, I joined the team, the Orion 2 team, in the summer of '62, and I think at that time the basic design had been completed, including the design of the extracode system, and the prototype was being assembled in West Gorton. It wasn't when I joined in August in that process. It was pretty soon after I joined, before I knew much about the machine anyway. Now, when I joined Ferranti, the only machine that I knew much about was the Mercury at Manchester University, which I'd been programming during my 3-year research stint. in PIG, in the assembler code, so I knew a fair amount about the internals. And my initial reaction to the Orion 2 was what has already been said. It was such an enormously complex machine compared to Mercury. And in fact, it was also a pretty fast machine. I think it was about 5 times faster per floating point, where clearly its raison d'etre was the commercial aspect rather than the looking at its customers, rather than its floating point. But it was still 5 times faster than Mercury's floating point. I joined Maurice Hill, who I think was responsible for the extra code programs. Although most of the design for the extra codes had been done, little of the coding had been done, and within a month or two, Maurice left to work for Coopers, so I got involved with doing the extra codes. There was one other programmer who also helped the logic design team. That was John Bradbury, who joined a little bit after that. And between us, we finished writing the extra codes, got them working, assisted the engineers in debugging the microcode by writing programs to test the particular area where they had problems, etc. Tried to make all the Orion 1 engineering test programs that were relevant work. Wrote new ones to cover gaps where there weren't any test programs. And then finally helped the ONT team when they came to try and run well, I've got it down as the Orion monitor program, but it's the organisation monitor program, is it?
Yeah. There have been differences for opinions.
Right. Well, I'll call it ONP. When they came to try and run ONP on Orion 2. So, what am I going to cover? Firstly, I'm going to try and define what is meant by the term extra code. Then I'll talk about why they were used on Orion 2. Then I'll say what was extra coded on that machine, so which bits of it were put into extra code as opposed to hardware. And finally, I'll talk briefly about how the extra codes were implemented and say whether I think that the approach was successful or not. Right, well, the normal definition of an extra code is that it is a sequence of machine instructions used to simulate a hardware function. I think this describes Orion 2's use pretty accurately. I've been trying to find out, without much success, where this term was and design strategy was first used. I thought it was on the Ferranti Atlas, because I'd been at Manchester, of course, I knew a bit about that. It had been designed there in the late 50s and early 60s, and I think the pilot atlas was first running in 62 before I left the university. Does that sound about right? Yeah. Certainly it was running before Orion 2 was running, so it's ahead of that. Recently, though, somebody else mentioned there were extra codes used on EDSAC2 at Cambridge. But I haven't been able to find out anything about that machine, or whether its implementation was consistent with this definition, or even when it was initially operational. Does anybody here?
Operational, I think it was 56.
Right. So it is well ahead of it.
I think I would feel that the term extra code had been familiar, probably from that for a long time. I'm not certain, I wouldn't be certain about it.
Anyway, why did Orion 2 use extra codes?
I mean, what sort of hardware function is this, are we talking about?
Well, I'll come on later to say what it did. All the extra codes on Orion 2 were used for basically the input-output area. Once you've got a framework there, you can use it for other things.
Yeah.
Anyway, I'm going to talk about that later. Well, the machine instruction of the Orion was a word of 48 bits, as we've covered, with 5 function bits. And it was a very extensive and highly complicated order code.
6 functions.
7.
You said 5.
Did I? Oh. It says 7 here. Sorry about that. Anno Domini. No, wrong way up. Just to give an example, the program's reference manual, in order to define the 101 instruction, gives that flow chart. I'm not expecting anybody to read it, but just the extent of the complexity for one machine instruction that is shown here. This, in fact, was to do with the conversion of card image data. There was a similar one. One was to do with card reading and the other was to do with card punching. Quite an extensive instruction. So, the Orion input-output design was very sophisticated and expensive to implement. In this area of complexity tackled.
You mean Orion 2?
Orion 2, yeah. So, when I say Orion, I mean generically, it's an expensive architecture to have to build and commission. And I think one of the main reasons for the extra code, Ted, you can correct me if I'm wrong, was it was seen as a way of reducing the cost and timescale involved in producing a machine that could be delivered to customers.
Absolutely.
Save a lot of time.
And after Orion 1's delays, it was really essential that we could do this. In addition, I think it was believed that by using extra codes, you'd end up with a design that was more flexible and would be easier to upgrade and enhance. And in fact, certain upgrades were done between the original prototype and the first machine delivered to the crew. Not that they affected extra codes much at all, but there were enhancements being done even then. Right. So, what was extra coded, as somebody asked earlier? The bulk of the extra code programs were to do with the input-output instructions. The objective of this, as I've said, was to reduce the cost of the I/O subsystem. As well as eliminating the microprogramming of the complicated instructions to do with input-output, it also eliminated the need for hardware lockout testers for every peripheral apart from magnetic tape and drum systems, which were too performance. The performance required by these systems was too fast to enable this to be done, other than the way it was. The lockout tester's effects were simulated by the extra code routines using a buffer associated with each peripheral in the extra code working space. For output devices, this was fairly straightforward. For example, when a line is sent to a line printer, the extra code copied it to a line print buffer and the program was allowed to continue. For input devices, it was a little bit more complicated than that. But fortunately, the Orion design already ensured that all input devices had an accept button, which told the operating system that a new file on that device was to be loaded into the machine. This was used to prime the relevant extra code routine to refill its input buffers and throw out what was already in them, so that subsequent requests for data could be fed from that new source. Fast peripherals, as I've already said, they still had their own lockout testers, but these were loaded and set into action by the extra code routines. Of course, once a framework of extra code is in place, any rarely used but complicated order code that can sensibly be performed by the extra code system. So extra codes handled fixed to floating point conversion and its inverse. Floating point standardization and justification orders were done by extra codes. Extra code was also entered in the division orders where the quotient appeared to be out of range so that it could detect and deal with some particular cases, rare cases, in which the quotient isn't actually out of range. Finally, there are some obscure situations which I can't really remember, where extra code was entered from some other instructions. The principle was that if it happened only rarely, so that it wouldn't impact performance, certainly wouldn't impact acceptance testing, and it was expensive to handle in the hardware, then give it to the extra code to sort out.
Had that already all been decided what was to be extracted by the time you joined?
I think so. There might have been some grey areas in these other, I mean, I think there was certainly division I've already mentioned. Whether that was decided beforehand, I'm not quite sure. I remember it sort of coming late to me on the scene, but it might have been decided and nobody had told me. And I think there were some other conversion orders where that was similar. So I can't be positive, but I think so. I think it was decided beforehand. So how was it implemented? Well, there was a special extra code mode of operation that was initiated by attempting to execute any of the extra coded instructions. A typical Orion 2 was expected to have 8 or 16K words of memory, although in fact they all grew, as computers do, when you actually come to use them. 32K, of course, was the maximum memory size. The Orion monitor program used the first 512 words, and on Orion 2, the peripheral hardware and the extra code programs used a region consisting of the next 1.5K. So the first user program usually started at location 2K. A lot of each of the peripheral devices actually had a word in memory used by the hesitation control. So it wasn't all extra code programs or buffers that occupied that space. It was sometimes some of that the hesitation system also used in space, although very little, I must be fair. One of the effects of running in extra code mode is that lockout and reservation testing was suppressed and entry to the timeshare was prevented. This meant that once extra code had been entered, it was guaranteed that it would not be interrupted until it had finished. In fact, it was arranged that the computer died if you had an unexpected event so that it could be used for debugging purposes. So it was pretty important we didn't get it wrong. Finally, in extra code mode, the 64 accumulators of the instruction set started in location 512, i.e. at the top of the OMP space. On entry to extra code, the hardware placed details of the instruction causing entry in the first few addresses after 512. So A0 contained a non-zero value in extra code mode. 512 to 516 was the details of the instruction. And the first instruction actually obeyed in extra code mode was executed from 517. The first thing this program did was fairly logical. Did a table lookup using the function bits that had been put into 513 in a convenient format for this purpose in order to be able to branch to the appropriate routine. All right, when in extra code mode, several instructions had special effects. These were mainly instructions of group 2, which weren't used by the extra code routines anyway, or instructions that were otherwise illegal. For example, there were instructions that loaded and unloaded the lockout registers and set them operational. Other instructions enabled the programmer to interrogate a peripherals control unit to find its status, or to send commands to it to initiate it transferring data. And then there are other instructions that enable you to set various indicators used by the operating system when exiting from extra code control, like peripheral lockout and things like that, peripheral incident. There were other fairly simple instructions that were just for converting or moving data sent to or from peripherals. So some of these were designed to do some of the conversion for card image data. I mean, it was a twofold process. The hardware produced the data in one form. The extra code converted that to a form that the 101 instruction that I showed earlier then converted it into a format that the programmer could understand. So there were two layers of conversion between what came from the card reader or card punch. Its view of the world and the program's view of the world. Right, other instructions, yeah, we're talking about peripherals. Oh, line printer, there was another instruction used to present the data in the correct form for line printers to process properly. Right, so, was the strategy successful? Well, I think it was successful in that certainly the first production Orion 2 was installed in the Prudential's offices in Holborn and handed over to the crew in early December. I've got this memory of 1st of December 1964, but it's probably a convenient number. It was certainly early December 1964, and I think it was on the planned date. I don't think it slipped at the last minute at all. I think the first Orion had been delivered about a year earlier, so clearly if Orion 2 was to have a future, it was as a successful upgrade rather than a replacement for that machine. Sorry?
February 63, I think the machine was delivered, but it didn't work for him. I didn't want to hand it over until about May or June.
Right.
You
So it's about a year and a bit earlier.
I'm sorry, I don't recall the turrets machine at all. So as far as I'm concerned, the prototype was assembled in Lily Hill, Bracknell, and delivered to the crew in October 64.
Yeah, and then we had periods of commissioning and acceptance testing,
Yes,
and the formal handover.
I haven't the actual date.
The signature of acceptance was, I think, the 1st of December.
I think I'll go with that.
Roughly to schedule.
2 weeks ahead of the deadline date for a 4,000 a week penalty.
As I said earlier, I'm sure debugging the peripheral hardware was a lot easier with extra codes than it would have been if we'd had to use arm's length approach through the microprogramming logic. So from that point of view, I think the strategy of using extra codes was a success. However, in September 64, shortly before Orion 2 was handed over to the Prudential, the ICT 1900 series was announced, and I think the rest is history. I was interested to see the list of Orion 2s put up earlier. I thought there were only 5. I got one of them wrong. I thought it was Norwich Union that had one rather than Legion's. So I stand corrected. And of course, the prototype was used extensively for software development in Lily Hill afterwards, wasn't it? But I'm sure if it hadn't been a blind alley, we would have sold more machines than were actually installed and sold. So that was the extra code system. Anybody got any questions on that?
Did you do any Sterling conversion?
There were certainly conversion orders, but they were not extra coded.
Oh, really?
You didn't really...
That was not good. I don't think so, no.
It was a binary machine, not a decimal one.
No, but it,
There's a mixed radix conversion order there, wasn't
I
there?
think that was it the 101 or
Yeah.
104? One of those.
Oh, yes, one of those.
It's not 101. They were card image. I'll have a look. I can't see it. Right.
I indicated earlier that there's a very key link between the hardware product and the users. We're very pleased with the machine. That was the Nebula language, and to tell us a little bit about that, we have Mark Roach. Mark came from yet another background. Everybody came from different backgrounds in the Orion 2 software and hardware teams. Mark joined from Jesus College, Oxford, from memory, and when he actually got to Lily Hill, he had to find himself digs, which happened to be the same digs that I was in. So I can't speak from first-hand experience about the tremendous effort and dedication he put into writing his parts of Nebula. So, Mark, over to you.
Right, thank you very much for that introduction. I was called up by Frank out of the blue a few weeks ago. I think probably because, although we hadn't seen each other for 40 years, he had remembered that when we shared digs, I happened to be working on Nebula. There are many other people far better qualified than I am to talk about Nebula, and I hope that those former colleagues and others in the audience will certainly chip in if I'm in any difficulty. Basically, I joined with absolutely no experience of computers at all, having graduated in mathematics. I joined Ferranti in October '61, straight into the Nebula team. I think I was the fourth or fifth person to join that team, which had probably been in existence at that stage about a year or perhaps a little bit more. And I always suspect, and there are probably people around here who can confirm this, that the original idea was that Sandy Fraser would produce Nebula in a year or so with a little bit of assistance. As I think I will tell you in a moment, the project, I believe, when Sandy left, which was at the same time as I left the team, and we had working versions of Nebula with customers, had probably consumed about 75 man-years, because at one stage the team was 33 strong. So in many ways, it was a very interesting and very pioneering project, certainly for me as somebody who didn't know what he was getting into. And I think one of the things we've heard today, we've talked about the division between North and South in Ferranti, the division between programmers and engineers. I must say, this is probably, I don't think I have attended a meeting as somebody with an interest in software, a meeting with so many engineers in it, as I have today, and I'm certainly learning things that as a very junior programmer in the Nebula team were completely foreign to me at the time, so it may have taken 40 years for me to catch up, but I hope I have something useful to say about Nebula. I'm not sure, Frank, how long I've got. I've prepared quite a lot of material, but I shan't bore you or attempt to use it all, but I will start off, I hope, by telling you, I think that Nebula stood for Natural Electronic Business Language. Like some people might have thought it stood for something else, New Electronic Business Language or whatever. As one of the first technical writer who wrote who started work on the Nebula manual pointed out, Nebula has only one anagram, and unfortunately that is unable. The decision, as I'm sure Ted was part of it, and probably knows far more about it than I did, and possibly George Felton as well, the decision, I think, was taken in 1960, at a time when COBOL was only just being specified, and was regarded, I think, as something American, something that Ferranti would have no control over. And it wasn't really in the spirit of Ferranti to use something from somewhere else. But also, I think the important thing in the selling of selling of Nebula, particularly to Orion's commercial customers, was that they were going to be very close to the designers of nebula, and that was particularly the case in the case of the Prue. The Prue worked very closely throughout their period when they were using nebula and before, while they were waiting for their machine and looking forward to the 4,000 a week penalty clause. So in many ways, the language was designed for the customer. And we've heard a bit from the engineer's side and from the microprogramming side about the problems with punch cards. There are people here who know far more about punch cards than I do. All I ever learned about punch cards was when Ferranti in Newman Street had taken on somebody who used to work for IBM, and he gave us a talk about punch cards. And the message seemed to be, you keep them in boxes, if you look after them, they'll look after you. But the complexity of dealing with people like the Prue had 30, they had two types of business, OB and IB, industrial branch and ordinary branch. I always get them mixed up, but I think the industrial branch was the man from the Prue going around to collect a penny a week. They had 30 million policy holders, or policies. Each policy was represented by a card. They had a room far bigger than this with 30 million cards in trays on them. Some of those cards were 90 years old. These life policies do go on for a long time. And they had a variety of punching conventions for the cards. Some of the cards, I mean, some of the data was actually written on the cards. You know, when new information came along partway through the life of this card, they couldn't get on. They handwrote it, and all that lot had to be handled, and in the end was converted to Orion. So it was, as we've heard, Nebula was designed with users in mind who had some very complex tasks to handle in terms of cards. Nebula also had a number of other features, but if we can just move on, the structure of a Nebula program, similar, I guess, to COBOL. The distinguishing feature, though, is that the data description was in two parts: a physical description and a logical description. And as I understand it, and others can probably confirm this was a unique approach, which certainly COBOL wasn't taking, and is certainly one of the things that made Nebula particularly suitable and powerful, and really sold it to the Prudential and others. Ted, you were involved, I think, in the original design. You certainly wrote a paper with Sandy and Peter Hunt on Nebula, which I've borrowed from, as you'll see in a little while. Were those basically the reasons why Ferranti decided to go for Nebula?
Well, my understanding was that there wasn't a COBOL data description yet. So
No, there wasn't. No. That's right. Yes. And COBOL barely existed.
Yeah, well,
yes.
I think COBOL was all right for specifying computations once you got to.
That's right. Yes.
But we had to do the data description.
Yes. Right. I'm going to so that we are able to leave before closing time or before opening time tonight. I'm going to skip or drop out with some of the details, but I've certainly got some slides if people have questions and want to ask questions, and I may well be able to illustrate the answers. Just to give you an example of what a bit of Nebula looks like, that is a piece of Nebula procedure description, which is taken, I think, probably from the paper that Ted and Sandy Fraser and Peter Hunt published in the Computer Journal in late 1961. I was always rather amused by the fact that, as I said, I joined Nebula team really completely green in order to write and work on something called the Compile compiler, which we'll come on to in a minute. I can remember an enormous debate going on as to whether I should go on a Nebula programming language course or not. I went on about 3 days of it, and then they decided that if I stayed the full week or the full fortnight, Nebula might slip a bit, and so perhaps I should get back and do some real work. The real work I did consisted, we'll come on to it perhaps a bit, for a whole year I wrote programs on squared paper, and these are almost the first bits of program I'd ever written, apart from some stuff I did on Pegasus when I first arrived, for a whole year without putting it anywhere near a machine. And so I had no idea whether what I was doing was going to work or not. Maybe the fact that I was only allowed to work as a programmer for 3 years before I was sent off to go and look after customers may mean that it wasn't actually terribly good. And I don't know to this day whether my contribution was significant or not, but I think it's quite interesting, and people today would think this is quite extraordinary, that you can work for a year without knowing whether what you're producing is going to work. And of course, when you did get to the machine, we used to we first of all worked on Pegasus, but then we were testing on Orion, and we'd have 15-minute slots. If you were lucky, you would get 4 shots on the machine over a 12-hour period. We worked when the machine was available, none of this having a machine on your desk, because remember, as a new graduate, I was actually quite well paid for new graduates in those days. I was getting £16, 10 shillings a week. The machines I was working on were charged out at £250 an hour. That I think puts these things into perspective. Anyway, there's a bit of Nebula program, a procedure description, and here's a bit of logical description for part of a file on which that program works. So to many, it probably doesn't look that different from COBOL. I think one of the amusing things was seeing a Nebula program written in Swedish. Several of the machines, as you know, were sold in Sweden. And actually they were quite sensible, except of course all the names were Swedish. Okay, so that gives you a little bit about the Nebula language. What was it supposed to run on? The minimum configuration it was designed to work on was a Franti Orion 1 with 8K words of core, 2 drums, 4 bank tapes, paper tape reader, and a line printer, or if you're lucky, or alternatively a paper tape punch. A pretty minimal configuration compared with today. What we have, of course, heard earlier on is the fact that Orion 1 wasn't the great success, Orion 2 was, and of course, in practice, the successful application of Nebula was almost certainly the cruise, and that was running on a machine which we've heard earlier was five times as fast, 5 times the power. If I can say that the first time I put through a page of Nebula through the syntax analysis process, this was on the Orion 1 at Turitz in Gothenburg where we were working. It took 45 minutes to do the syntax analysis on about 3/4 of a page of programs. That perhaps gives the idea of how slow it was. It was slow on Orion 2 as well, because I think one of the comments made by the crew, and my experience certainly working with customers, was that any compilation took a very, very long time, which was why Peter Hunt was quite happy to send me to hold Metalbox's hand for about a year. Looking back, I'm not quite sure what we did other than wait for things to compile, the compiler to fail, and then send enormous great printouts back to Bracknell. Okay, the Nebula compiler, designed by Sandy Fraser, and the compiler itself was written in a language called COMPL, which stood for compiler language. And the Nebula compiler, as delivered to customers by the time it was finished, consisted of about 1,000 separate subroutines, or about 250,000 words of code. COMPL was compiled into SIL. SIL, I think, stood for Compiler Interpreted Language, and SIL was interpreted on Orion. The COMPL compiler was also written in COMPL. At least the first version of it was hand compiled into SIL, but then since one was actually able to compile it and maybe produce some improvements. Now, SIL interpreters were written for Pegasus and for Orion. As we've heard earlier, I think the Orion prototype in Manchester wasn't available to programmers until sometime October 1962 or thereabouts. When I joined in October, one of the team members, John Francis, had just completed, I think in 6 weeks, a SIL interpreter which ran on Pegasus. And so we were able to do some work on Pegasus, but we very quickly ran out of capacity on Pegasus. And that's where this sort of year of writing code in pencil on squared paper came in, as far as I was concerned. And it was the year before I went to Manchester. And like Malcolm just now, it's the first time I've been north of Watford, or almost. Okay, so that was the Nebula compiler, then written in COMPL, COMPL in turn compiled into SIL. I'll just give you, if I have an example of what those things look like before we move on to something hopefully a little more. Yes, just quite quickly, COMPL was both an operating system and a language and compiler, I guess. It operated in a data store of about 250,000 words, and it stored this single-level store of 256k words or thereabouts in blocks on tape. This is where your 4 tape decks come in. And of course, those tape decks were very heavily exercised because we tended to be accessing this fairly randomly, although we did have things we could do to try and make it less random, but in practice it was pretty random. Some of it was obviously available on drum, and the most recently or most frequently accessed blocks would 12 blocks would be in core. COMPL had a nest of 7 words in 0 to N6, which were in a push-down stack, and then the COMPL object programs themselves were kept in a chapter store. So that in very brief terms is the structure and how COMPL was stored. Somewhere amongst all that lot, there was a SIL interpreter. Right, the COMPL data store. It was a list processing language. My third day at work with Ferranti. My first day, I was given the COMPL manual. No, sorry, the Nebula manual to read, and with no previous computing experience whatsoever. I'd arrived at Oxford about the same time as Oxford's, was it a Mercury or a person? No, Mercury. Mercury. But it was for scientists. And I went to one lecture about it, but as a mathematician, a pure mathematician, it really wasn't of any interest. And so I came to this a complete novice. But my second day, we went to the maths lab at Cambridge, and we went to attend a lecture on Lisp given by John Eilert, which was very relevant, and it gave me a useful insight into what I might be about to be doing. So a 48-bit word, in SIL and COMPL terms, that word was divided into 5 fields. Fields A and B were normally for addresses, so you build up a string. If you were at the end of a string or tree, then m would be set equal to 0, otherwise it would be 1 to indicate the day as an address. So you were able to construct and use fairly complicated trees and strings and with the occasional block to represent what you were doing within the compiler. What you had to remember as a programmer, if you asked for some store, you had to jolly well make sure that at the end you freed it, because you would very soon find everything would grind to a halt, because and when one discovered that other programmers had failed to free store, you very quickly knew, because you had no space left in which to work. I won't try and explain to you the syntax analysis process, but basically you were able to define the syntax of sentences and statements, whether it was nebular or whether it was compl. There was a common syntax analysis process which took the input language, the language you were inputting, and constructed something called an analysis tree against the class definitions which define the syntax of the language. And just to give you an idea of the tree, that is an analysis tree for a statement of the form: if A equals B, then set C equals D, then go to E, otherwise go to F. Quite interesting that Sandy chose, or maybe it was Ted, to use the word otherwise rather than else. I always felt it was very inelegant that we had only 9 reserved words. In a way, going back to something that Ted was saying, it would have seemed more elegant to have had 8 rather than 9. And the 9th one was otherwise, which is far too long for anybody's comfort. Everything else fitted quite, was sort of four characters. Anyway, that gives you an idea of the sort of things that we were working with in writing both the nebular and the compl compilers. Here is a short, quick example of a compl program. This is one for compiling a condition statement. I guess in compl. You can see that you were able to push down and pop up your nest, and so you had a fairly. And this program is recursive because it performs itself, quite capable of performing itself in several ways. Perform procedure, ETB, whatever, is. I'm not sure that it can't be improved upon, because that statement appears several times. I'm sure there would be a neater way of doing it. This is a procedure which is buried within the syntax and within the analysis tree for compiling, for used in the compilation of that particular statement, which that analysis tree represents. And so you could quite easily, I mean, recursion was an important feature. It was also something that, of course, slowed everything up terribly. And as programmers, working so far from the machine, without any contact with people who understood the real world, you can imagine that elegant as it all was and theoretically beautiful, and in many ways, the technology, I think, was not quite up to what we were doing. But there we are. Okay, moving on very quickly, SIL. SIL was a language which was interpreted. A SIL instruction consisted of a function, an X address, a Y address, and theta being an operand. The X address could either be a nest word, which was something known to compl, or an X register, which was, I think, X0 to X7, I think there were 8 of them, which was known only as effectively working space for a compl, for a SIL program, for the for the compiler. For instance, the function 3 was multiplication, so that example at the bottom would be an instruction which sets the contents of the x register 1, x1 equal to the contents of nest 1 times the contents of the word whose address is in the B field of N2 or something like that. I think I've got it right. Okay. I think it is probably interesting now, if we've got time, just to sort of give you a history of the nebula, starting in 1960, when Franti made the decision, and work on development started at Newman Street under Sandy Fraser. As I said earlier, my guess is that if Sandy said, oh well, it'll take a year and a bit and I may need somebody to assist me. By the time I joined, when I joined, there were 5 people. I think there were 4 there already. I think Ted Brownheltz was probably floating around somewhere. I remember the name, I think I remember the face.
I just floated off to Lily Hill.
And you'd gone to Lily Hill, yes. The Nebula team floated off to Lily Hill in 1962. This came as a bit of blow to me, as I'd only been working in London. I just found somewhere to live after several months, and I was set up in a flat with some former university colleagues. I remember I went to the loo on the 3rd floor, or whichever floor the loo was on, and I came back from the loo and I said, "Oh, you've just missed a meeting. We're all going to Bracknell." To me, that was a bit of a blow. But anyway, in August we all went to Bracknell. I think my removal expenses were £4.50 or £4.10. Several years later, Franti or ICT moved me to London, and then they moved me back again. And I can tell you, it cost a lot more than £4.10 on those future occasions. But as you'll see, in '62, we began to use the Orion 1 prototype in Manchester. This involved programmers going up to Manchester to work. We had a shift system. There were 3 shifts. The shifts were allocated one to programmers, which I guess probably included the old team.
Yes.
Yeah. Nebula as well, sharing that shift. One shift for the design engineers, who were continually making modifications because after all this was a prototype, and another shift for they were training maintenance engineers, I think. Is that right, George?
I think so.
I think so. Anyway, as a programmer, it was inevitably we had a shift, whether it was 8 o'clock in the morning, 6 o'clock in the afternoon, 4 o'clock in the afternoon, or whenever, midnight. Your shift always followed an engineering shift, which means the machine didn't work. and I can remember once a colleague and I, Derek Gears, he had a car. I didn't. Everybody else had a car. Frank had a car because he used to give me lifts to work, except for the morning he forgot to take me. I'm still not clear whether that was absent. Anyway, so I mean, I can remember one day we deliberately said, well, it's been disastrous this week. We won't go in next shift. So we went off to North Wales for the afternoon or the evening or whenever. And of course, when we went back the following day, they said, "Why weren't you here? The machine worked beautifully." Well, we knew why it didn't work beautifully. It's because the Nebula team actually made more demands, we always felt, on the hardware than anybody else. There's a mistake in that, I think, but in 1962, Alan Roussel, who went on, was one of the after salesmen, I think they were called, and he wrote a note which appeared in the Computer Journal, which reported that there were 10 Orion commercial customers writing programs in Nebula. Now, those are 10, but I realised that in compiling that list of 10, I left out the Prue. So one of those, sorry, I've misspelled Trig, I think it's Trig Filmier, isn't it? But one of those customers presumably was not intending to use Nebula, and I don't actually know which one it was. It might have been the bank, or Cadbury's.
Yeah.
Ah.
Used, Nebula.
Oh well, yes. This was an intention.
Yes.
Yeah. Yes. I'm sure you're right. But few of those actually went all the way and stuck with Nebula. And as I think we'll see in a moment, it was probably probably only the Prue, although I'm not quite sure about South African Mutual.
Well,
They did.
yes.
Yes. But there was a difference between you using or attempting to use, as Alan wrote there, and actually seeing it through. That also gives you an idea of who the customers were. I think we saw a list earlier on. Having got fed up with the prototype in Gorton, and also working at night, and even somewhere where during the day the sun didn't come out, we went, four of us, I think initially, went to Turitz in Gothenburg in Sweden. Their Orion 1, we think, arrived in February. It was more or less commissioned by the time four of us arrived in May. And the trip out there was quite interesting. I think Alan Thompson, you went in an aeroplane, wasn't it, to the Ferrantis, with a whole lot of tapes. The heaviest and most valuable commodity was not the people, it was these masses of magnetic tapes. And I don't know if it's the senior or more important people, although it seems a strange logic, went with the tapes in the plane. I was very happy that not to go, because it sounded as if you had a very hair-raising trip skimming over the waves from Manchester to Gothenburg. Is that right?
It was quite delightful, right?
Oh, it was delightful, sorry.
Nice day.
Oh, okay.
Nice view.
Anyway, we worked. Turitz had the machine during the day. We worked through the night. It wasn't so bad because it only got dark for a couple of hours, if that. But the Swedes used to come in after break, at 8 o'clock in the morning, and I won't try and do a Swedish accent, but how is your software going? We're looking forward to Nebula, and it wasn't the best environment in which to be working in, but it certainly got things moving, because we had a machine to ourselves, and it was a lot more reliable than the prototype had been. We then came back to Bracknell in September '63. We were quite amazed to find that the team had doubled in size, and there were all sorts of people we'd never seen before who were busy writing. I guess they were writing bits of the Nebula compiler in Compil, so we were quite glad that we came back with something which we thought worked reasonably well. We then got time on the machine at Harwell. And by the end of that year, there were 33 people working in the team. We were all based by that time at Lily Hill in Bracknell, but the machine we were using was Norwich Unions at Norwich. So we spent some time working at Norwich, and some of us used to sleep in our van in the car park, not me. But then I think they got fed up with people staying in Norwich, and so there was a car service where jobs were taken up each night. I believe that the first official release, I think people were using Nebula before that, but in my recollection, April '66 was a fairly key date. It was the date that I moved on to something else, but more importantly, it was the date that Sandy Fraser moved on, and it was also, I think, marked the release of what I would regard as Nebula Mark I. Now, my personal knowledge of Nebula ceases about there. I did speak to Keith Noble over the phone. Over the phone the other day, and he was able to confirm 1 or 2 dates to me after that. But basically, from 66, the crew were using Nebula seriously from 66 to, well, they started using it from the very beginning, but I think we can say that their use of it really was 66 to 75. In 67, Ewart Willie was reporting that they'd completed a suite of 39 programs of that size and were working on 2 more. And Keith Noble told me the other day that Nebula support ceased in 1970, and I think Mike Pickett, who's here today, can probably confirm that. And although Prue had been predicting that they would switch off Orion a bit later than that, I think that it was they switched off Orion in their Orion 2s in 1975 and replaced them with 360s or 370s. Nebula, a user's view. This inevitably is the Prue and Ewart Willie, and I've tried to summarise some points that he's made in the past. Back to the point that it set a standard which couldn't be met by COBOL, and nor could PL1 meet it. Strong in data handling. Variable length records and data items, I guess it was ahead of its time in that respect as far as the commercial language was concerned. The Prue, obviously, like the printing facilities and the diagnostics and listing for programs, they felt were good. So the Prue were definitely pretty happy with it. And before finishing, I think I'd like to pay a tribute to Sandy Fraser. Sandy was I guess, with some assistance from others, but really saw Nebula through and was the main designer and manager. I think he probably joined Frant in about 59. He left Frant in 66, spent 3 years back in Cambridge, and then had a very distinguished career at AT&T Bell Labs, where he rose to be chief scientist. And I think he was a presidential advisor on all sorts of other things. He now is retired and has his own not-for-profit research company. The final word, I spoke to Ewart Willie over the phone, and Nebula a tremendous success. I think that without Nebula, Orion 2 would not have been regarded as a success. Orion 2 and Nebula, Orion 2 made Nebula work, and Nebula made Orion 2 work, if I can put it that way. It's only a pity that in the end it was really, we think, only the Prudential who used it, and that despite the fact that there were many very important design features, both in the language and in the way in which it was implemented, it was a development and implementation which never went any further, which applies, I think, to a lot of what Frankie did. Anyway, thank you very much. Any questions?
Well, thank you, Mark. That was very interesting. Now, there's a slight deviation from the programme as originally put together. Today we have Gordon Harvey with us. Gordon, where are you? Someone at the back. There you are. Gordon has very kindly brought some slides along, and I think at this point I'd like to invite him to come and show them. For those who don't know this, Gordon was in fact the manager of the entire hardware part of the Orion 2 project, with 2 subordinates, Jack Templeton and Peter Harold. I reported to Jack Templeton, but Gordon is the man, in fact, who carried the can. So here he is to tell us a little bit about it. Slides have been preloaded. We shouldn't have too much of a problem.
I apologise at this point. I have to give another lecture at 6 o'clock.
All right.
Hamish will take over the chair at this point for the rest of the time. But thank you for a fascinating afternoon. I'm sure the rest of the time will be equally. But I have to give a lecture, I'm afraid, to my students.
Thank you, Roger. I'm sorry if we've taken a little longer than people expected, but let's talk the story just now. So here we are, Portugal. Well, I hope this will be a bit of light relief after some quite heavy material. This is really to give a bit of flesh to what we've been hearing about. And I think the main message is, compared with today's computers, how vast and bulky and extremely difficult to deal with were the computers of 40 years ago. That's not a very clear slide, I'm afraid, but it represents a view of the back wiring of Orion 2. It comprised 6 cabinets, each with a footprint of about 3 foot by 2 foot. And there was a separate power unit, which was 2 such cubicles. And that, of course, doesn't take account of the punch card equipment and so on. There were 10 tape decks, which I think were Ampex TM2s, as I recall. Did anybody know any different?
Well, they were like TM2.
Still too on.
Sorry?
There's not enough lights out. That's it. That's it. That's it.
And that represents not a very clear picture. It's not very well focused, I think. Of the Orion 2 control desk. I think that's Brian Pert, for those who were at Lily Hill at the time. Oh, yes. And people who knew Lily Hill, this will perhaps be quite a revelation of the way it was. And for those who didn't know Lily Hill, well, that was the room above there was near the main conference room. And during the summer, the loudest thing, apart from people nattering in the conference room, were birds chirping away in the magnolia tree. It was a delightful place to work. And I think that contributed something to the atmosphere of the team, who were working together very well. And that was the process of loading at Lily Hill, the front of the building, loading the 2 3-section parts of the main computer. I think that's John Travis. Some of you will remember John and June.
Jeff Stubbs.
Is it Jeff Stubbs? Oh, okay. It's
Brian Travis.
I thought it was John. Never mind.
I think he's got bigger feet.
We developed some quite sophisticated handling equipment for this gear. I think one of those cubicles, a set of 3 cubicles, would weigh something approaching a ton. And there was one load about to leave, being strapped up. And there it is again. And this represents a Sunday morning in the Prudential building in Holborn, Greville Street. The road had to be
coned off, closed completely by the police. And we had this enormous crane to get the thing off the lorry and into the building, which meant removing a window section. So there it is, one of the sets going in, almost going in. There it is, nearly in. And I think this is the last one. Unfortunately, I don't have a slide of the complete finished installation. So this merely represents the final stages of commissioning, or rather, no, the early stages of commissioning when the thing was fully assembled, but not yet subject to test. And some of you will recognise the characters in that picture. Well, thank you. I thought it might help just to give a little flesh.
Right, well, that was a little life relief. I'd just like to now bring the overhead projector back, if I may, and summarise a very personal, subjective view as to what came out of the Orion project. So here goes. And this is very much my own view. I have to say that with a disclaimer. What we did was to create a fast, a large capacity storage machine. There were no less than 3,700 cards, 700 series cards, or packages in the final machine, and this really proved their technology en masse. There was one very satisfied UK customer about which we've all spoken, the Prudential Insurance Company, and one overseas customer from which incidentally we've had very little feedback, the insurance company in South Africa. For the Prudential, it was a workhorse for them. My understanding is for 12 years. I believe there was some parallel running between the IBM machines that were mentioned and the last Orion 2, as data was transferred from the Orion to the IBM machines. My understanding is the last one finally was switched off in 76, but it's probably correct, the other two probably went in 75. The whole project led to development of an outstanding commercial language and programming user interfaces, which Mark has described to us. And it also led to the realisation and efficient operation of multi-programming and time shifting, which showed that it actually worked. It was in fact the machine that brought it to reality. In terms of achievements, it took just over 18 months from my memory from, in fact, the go-ahead to the rollout of the machine, which was a fantastically short time scale, even with those heady days.
That can't be true.
Yeah?
September 61
Yes.
to December 64.
Right. So in fact, I've got it wrong, haven't I? I somehow thought in fact the go-ahead was only in 62. No, you know better than I did too. Because you've got the green light. Right, okay. So in fact it was 62, 63, 64, just over 3 years then. Right.
Was it actually running full belt, or was it a sort of insurance? Was it done as a sort of background insurance sort of job?
In case the Orion didn't want it, but well, partly that, as I said, partly as a way to keep the proof from cancer.
Yes.
Right. This is done from my memory, which clearly in fact is not as informed as others. So in fact we didn't quite, as I've indicated here, level played with the quoted yardstick. The quoted yardstick in computer development is often still quoted. Seymour Crane's colleagues designed the CDC 6600 in 18 months out in the wilds at Chippewa Falls in the United States. Miles from anywhere, which in fact led to complete dedication and concentration of staff. Now I suggest that in fact the Orion 2 team were completely dedicated and concentrated on Orion 2, but as you just heard, the timescale was pushed out a little from that which I remember. So there was in fact a slip in my memory, not that I was fully informed anyway. What came out of the project, again at a high level? Well, I personally believe, and I'm speaking from some experience as you'll learn in a minute, that the technology transfer from Orion 2, and the technology which TED particularly took to the United States in from memory, January 1964, to a then known company called Scientific Data Systems, led to the growth of that company. Two of the members of the Orion 2 team went out later to join TED, joined the company, Byron McLeod and George Rigg. Scientific Data Systems really was one of the phenomena of the 1960s. When the Sigma 7, which really was a world-leading machine, appeared, from that in 1965 or 66, almost 2 years, right, it was reported as being referred to by one of the Ferranti brothers as Orion 3, so you can judge for yourselves. However, the SDS machines were world-beating rates in the 1960s, taken over by Xerox in 1968. I understand from Ted he bowed out sometime around that time.
Excuse me, could you shove that up the screen?
Push it up. All right.
Thank you for standing.
Okay, makes yes, in 1968, Xerox decided that they wanted to buy into this newfangled computer industry. And at that time, I believe a number of people, including Ted, bowed out sometime around that time. He'll tell you rather than me. I believe the SDS story is such an important story that we should perhaps devote a CCS meeting to it sometime in the future, possibly a year's time. And if we do devote a meeting to it, and this is very interesting, there are very likely the 3 speakers on the platform or here on the platform today. Ted, in fact, who was a major part of the engineering and other activities in SDS. Mark Roach, who in fact had a Sigma 6 and ran it as the user, the speaker as the user of that. And myself, because I became the UK support engineer on the Sigma 2 when I moved on from Ferranti. So 3 of us got involved in SDS technology, which, surprise, surprise, was Ferranti derived. Okay, at a low level, what else came out of the project? Well, in ICL felt them was out of the project, as you might expect. What they got out of it was proof that the 700 series cars worked and were reliable and robust. They also, in fact, got design standards out of this project.
Thank you.
For the drawing offices for new and redesigned cars. I personally had to lay these down. I laid down the standards for track widths to reduce the curvature, to kill inductance, and other, in fact, important parameters on the 700 series cars, which came out of the Orion 2 project. Those were spun off from Orion 2 and the later research, and served the company well right to the end of double-sided cars in the 1900 series when they went multi-platinum. The fact that in fact nothing was ever heard about it means yet again it was a reasonable piece of engineering. You only hear about the bad pieces in engineering. The fact that you knew any problems. Right, the last point I just want to make is that the common hardware with the FP6000 ran all the field engineering stuff in the Orion 2 days on that hardware. They ran all the learning curve. So when in fact the FP6000 became in 1904, which it did, with a floating point unit in 1905, the field engineering stuff will run up to speed, and I still got a lot out of that. So there we are, gentlemen. That, I think, is the end of what I think was a reasonably successful story. You've heard the good and the bad, you've heard the side stories, and you've heard quite a lot about the internal workings of Ferranti stroke, ICT stroke, ICO. Thanks for your attention. I think at this point we open the meeting to further discussion, some of which we've had already. Thank you. One last point, I just forgot to ask to thank my co-speakers. When I was asked in fact if I could put the slides together, the answer was I personally couldn't, not the whole scenario. So I've got to thank my co-speakers for giving their parts of this story, which I think is very interesting. Mr. Chairman, now over to you.
Have we got any discussion that we want?
Microphone.
Have we got further discussion that we want to carry on?
Can I just say one thing? Gordon Howard, can you hear me?
Is it going on to the tape?
Oh, I see, in order to get on the tape, right. Oh, I see, I can just talk to it. I just wanted to say what an excellent computer design group we did have in Lily Hill. It was very able and very happy, and everybody cooperated together. One of the best groups, well, I haven't been in that number, but anyway, it was first rate.
Simon.
Yes, I was trying to dredge up my
memory of Atlas 40 years ago, various aspersions were cast against it. In particular, it was said to be difficult to tune. I think that might be a reflection on the fact that Atlas was asynchronous. The point contact business, I think the speaker referred to the first experimental transistor computer in 1954. One more point about carry and parallel adder. The Atlas used a symmetrical transistor, the SB240 in its carry path, which gave a complete add time of 200 nanoseconds, quite quick. I guess we may hear a little bit more about Atlas in subsequent seminars.
My name's Colin Merton. I was involved in the Nebula project, and two anecdotes might amuse you. When Orion 1 was first announced at Northampton College, which became Cambridge University, there was a rather nasty man who got up, called R.H. Williams, and said, there's really rather not a forward-looking machine at all. It's almost obsolete already. It's not very fast, it's not very powerful. George Felton got up and said, anything which works is obsolete. Another reminiscence from the Prudential. When we first helped the staff of the Prudential install Nebula, Chris Atkinson set up an operating system with a cycle of 10 magnetic tapes for developing the programs. And the Prudential said, this is a rotten system, we're experts on organizational methods. We can think of a much better way of doing it. Chris Atkinson said, I'm sure you can, but we've worked this one out and we really haven't got time to change it just yet. Could you please operate this one just for the time being? About 5 years later, one of the Ferranti staff said, well, we think we might have a better operating system. We can't change that, Mr. Atkinson said so.
One question from an outsider of the team. It looked to me as though the Orion 1 was not such a disaster as you predicted, since you managed to sell about a dozen of them. So, am I right in thinking the U2 was in some nature an insurance policy which actually wasn't entirely necessary?
Well, what I said before, it's partly an insurance policy, Peter Hall started it as, and partly he started it in order to keep the crew from cancelling.
Yeah.
Those were the two reasons.
He told me not so long ago that he started Orion 2 so that he could sleep at night.
Can I just come to a comment here? Orion 1, I think, was basically a very sound machine because the technology was such that it was going to take quite a long time to get it right and get every detail worked out. And it did. It took the best part of 5 years. Nothing wrong with it, but in the commercial and market and legal conditions, some other solution was required, and that led to Orion 2. So nobody's knocking Orion 1. It's a damn good machine. It was described to us by Chris a little while ago. But it did have a long time from conception to market, for very good reasons.
It was the hardware that let it down.
I wouldn't say it let it down. I think once the decision was taken to use neurons, you were in for that appropriate time scale. Yeah. And I mean, polite, I think, like that.
But it would then be obsolete.
Well, as you heard from Colin Merton just now, the moment the computer's through the door, it's obsolete. And that was still there. You buy a PC, it's obsolete when you get it home.
I think I'll give you a slightly contrary view, because having been at the sharp end of trying to keep the beast running, there are sods to run. I would say they more or less bankrupted Ferranti, both in the amount of effort in the field engineering organisation to keep them running, and in the manufacturing. West Gordon has spent an awful lot of effort sort of just to make the Orion ones that were delivered. If there had been a sort of more cost-aware and time-scale slipping-aware culture at Ferranti, it perhaps might not have gone on so long before the insurance policy that eventually was brought on by tenants. But if that had happened sooner, Ferranti would have been in a different position. The Nebula story was ahead of its time in one respect, in that it really hammered the hardware together with the signal level store, and that contributed to the slowness, the time, all the rest of it to get jobs, to get the compilation jobs through. If it eventually got through in Orion 2, if the ICT merger, if at the time of the ICT merger the sort of perception that Nebula was a success had been developed, then ICT could have then put a random access store, an obvious thing for disk storage. Orion 2 was crying out for disk, but that development, there were then into rationalisation of company activities, and some big decisions were made that the Ferranti on-brand machines weren't the way forward. I suspect Nebula got lost in that sort of policy, but that's sort of with hindsight, perhaps to counter such rules.
Further points?
I'd like to put two things on the record. One thing I should have said about the installation, the photographs that were shown were taken on the 19th and 20th of September 1964, and I think the handover occurred, as was said earlier, on the 1st of December. So that process was pretty rapid, as well as the development process itself. The second thing I think is worth putting on record, mention has been made of the FP6000. Perhaps not everybody knows that FP stands for Ferranti Packard in Canada, and I think I'm right in saying that the original so-called Griblons were developed by Maurice Gribble in Ferranti, Edinburgh.
So
Wythenshawe, okay. Were then transported or acquired by Ferranti Packard, and then came back to UK as the elements that were used in Orion 2.
Right.
Thank you.
Well, gentlemen, time is running up against us. It's been a fascinating afternoon. I think I would only, in closing, add one further comment, that we were very sorry to hear that Peter Hall wasn't going to be able to be with us, but we send him our best wishes. I'm quite sure that he would have had some very pungent things to say in closing about the relationships between engineers, customers, salesmen, if there are any, and that whole aspect of the Ferranti story. It's been a fascinating afternoon. Thank you all for coming. Look forward to seeing you again in the next session, when Donald Swade will no doubt be in his usual exciting form on Charles Babbage. Thank you all.
Thank you.